All right, Chem 107, it's a new week. We only have 2 labs left until you are free of me. Hopefully that makes you have a better day. Anyway, I also hope that you are getting out and enjoying the beautiful sunshine and not getting too hot. It's rather warm up here in Cottonwood. Anyway, I also wanted to say that everybody should be wearing a mask when they go out in public. It doesn't have to be a fancy mask. Just any kind of simple cotton mask will prevent you, if you are asymptomatic for COVID-19, from releasing virus particles out into the environment. Saying is, my mask protects you, your mask protects me. Anyway, that's a public service announcement from your friendly chemistry instructor. All right, now on to the lab. We're going to do reaction rates. I assume you guys have covered this in lecture or will be covering it soon. There's a couple things we're going to cover here. We're going to talk about reaction concentration, temperature, and then we're going to talk about catalysts. Okay. So first I want to talk about what has to happen in order for a reaction to occur. So reactants have to come in contact with each other. The reactants also have to react with the correct orientation. However, we cannot influence that. But what we can influence is that the reactants must have sufficient energy to overcome the activation energy. And I'm going to draw a better reaction diagram down here. Here we go. Here's our reaction diagram. I said better, I didn't say great. So here's our reaction diagram. We have reactants here. We have products over here. And they have to take this path over the hill. From reactants to products, they have to go to the top of the hill. And so what they have to do is they have to overcome what we call the activation energy. And that is that right there, activation energy. That's the energy required for the reaction to occur. And just so we're all on the same page, the difference between the reactants and the products, the difference in those two energies, that's really a bad line, that's okay. That is delta H for the reaction. We're not interested in delta H today, but just so you know. So there's that activation energy. That's a big hurdle to get over. So what we can do is we can add energy to the reactants. That can help us get over the hump. If we add energy to the reactants, that will help us get over that activation energy. One way we can add energy is by heating up the reaction. I kind of like to think of this as your car is out of gas down here, and you need to get over this big old hill to get to the gas station way down here. So adding energy would be like making your friends get out and push, okay? If you have your friends get out and push, you're way more likely to get over that hump and get over the reaction or activation energy and get over towards products. The other thing we can do is increase concentration. Now you might say to yourself, well, that doesn't add energy. But if we increase concentration, what does that do? Well, that just makes it more likely for collisions to occur. And statistically speaking, if more collisions occur, then more will have enough energy for that reaction to occur. I like to think of this as, driving in the Walmart parking lot. Maybe, hey, go there tonight. There's nobody out shopping anymore. But compare that to maybe last Black Friday. Black Friday parking lot is packed at Walmart, right? You are much more likely to get in a collision there when the parking lot is packed because there are more cars. There's a higher concentration. If you're more likely to get in an accident, then you're more likely for any of those accidents to be bad. Okay. So one more thing we can fiddle with in this is we can change that activation energy. How do we do that? We add a catalyst. And when we add a catalyst, we start at the same spot, but we don't go over nearly as high a hump, and we go to the same end point. So that is a different activation energy. Just draw it right to there. Maybe that was a bad color. Oh well. Activation energy with catalyst. Technically speaking, what it does is it goes through a different reaction mechanism and it lowers that overall energy. We don't care about the reaction mechanism stuff, but suffice it to say that if we have a catalyst, we go through a different path. That's the key. That's the pink. That's with a catalyst. Maybe I should have written that. The pink is with catalyst. And if we lower the activation energy, well, then there's just more molecules that already have enough energy to overcome them. Okay? So let's talk about the actual collection of data. We're not doing the, you guys figure out the pre-lab on your own. Collection of data is pretty simple. All you're doing is measuring time. Okay? Volume of solution B over the total volume. This all comes from the video or the lab. Then you measure time. You're going to need your own stopwatch. Just use your phone. And you're just going to write down test tube 1. How long did it take? 10 seconds, 20 seconds. Let's just say it's 10, 25, 32. I might be going in the wrong direction. It doesn't really matter. You're just literally writing down how long it took in seconds. Okay. And then they're going to do the same thing here. We're going to write down the temperature in there, and then again, how long this reaction takes. It's pretty obvious when the reaction is over. It goes from clear to dark blue. Okay. And then we're doing it again with and without catalyst. And all we're doing in any of these is measuring how long a reaction takes. Okay. One thing that students get thrown with, though, is if we have a fast reaction rate, that means the reaction will take less time. Just like if you travel at a high rate of speed, it will take you less time to get somewhere, right? If you travel at a low rate of speed, a slow rate, it will take you more time to get somewhere. Same thing goes for chemical reactions, okay? Fast reaction rate takes less time for the reaction to occur. Slow reaction rate takes more time for the reaction to occur. Don't get confused there, okay? Just some simple questions here. For instance, lower concentration solution B reaction go faster or slower? Just circle one. It's not hard. If it's less time, it went faster. Okay, and then a couple post labs. How did concentration affect reaction rates? Now here, I just want to point out a couple things. This sentence here, utilize your knowledge of reaction rates and collision theory to explain what is occurring on a molecular level. So I want to know, are the reactions occurring with more energy? Are they occurring more frequently? Have we lowered the activation energy? What have we done for both of these questions for these reactions to go faster? But we're talking on a molecular level. So talk about individual molecules. Again, are they reacting with more energy? Are they reacting more often because of concentration effects? Oops. I may have given an answer away. Are they, is the activation energy been lowered because of the presence of a catalyst? All right, that's it for this week, you guys. Just one more week after this. I hope you are all doing well, sequestered in your homes. I know it can be a lot of not much fun, but again, wear your mask when you go out in public, and maybe we can all get over this thing a little bit quicker. Have a good week.